We're looking at elementary statistics, section 9.3, two means independent samples. Okay, so within this, we're going to be looking at the discussion on the standard deviations. The two populations are known and are not assumed to be equal. Then we'll look at the other situation where we have two populations, standard deviations are both known, or the two population standard deviations are known, are unknown, but we're going to assume that they're equal. Okay, so really we got three different things going on in here. Part one really is talking about our independent samples with sigma 1 and sigma 2 unknown, and they're not assumed to be equal. Okay, so the two samples have to be independent of sample values from one population, are not related to somehow naturally paired or matched with sample values from the other population. So they have to be completely independent with what's working on. Now, we also have dependent variables where we talk about match pairs, where the sample values are somewhat how matched, where matching is based in an inherent relationship. Okay, so basically this is describing this section and then the next section, whether we have independent and dependent values in here. Do realize independent is we take one pool sample and then we randomly pick another one. Dependent could be talking about, we could be comparing one twin to another twin, and mental capacity in there, because twins are the closest thing that we could have to being yourself, only in another person. We could also look at before and after on like a drug study of values in there where they have to be matched up somehow. Okay, so that's where that kind of starts talking about in here. Once again, we're relating to that independence of what's going on. So, conducting a hypothesis test about two independent population means. Okay, once again, I kind of stated our null hypothesis, mu sub 1 equals mu sub 2, and then our alternative hypothesis, basically our mu sub 1 is less than, greater than, or does not equal mu sub 2. Once again, depends upon what claim we're referencing towards. In this, we are looking at a t for this. Once again, stipulations. Values of sigma are unknown. Okay, so they're unknown, and we do not assume that they're equal. Okay, independent samples, simple random samples. Sample size are both large. Once again, both have to be greater than 30, or they have to come from a normal distribution. So remember, we had a loose interpretation of what this was. This was not a strict interpretation of this for normality. We're going to be using a t-test. Once again, degrees of freedom, critical values, everything went in here. Degrees of freedom, smaller of whatever n value is. So basically, if we have one sample that has 40 in it, one sample has 30 in it, we're going to use 29 for our degrees of freedom. And that's basically what we're going to start testing towards. In confidence interval, once again, we're looking mu1 minus mu2 in here, and then we're going to have our values outside with our error that we have in here. Once again, the calculator is going to do everything for us. Now, you're going to have to keep track of what is used for what situation, because once again, we have t-tests, we have z-tests in here. Confidence intervals, t or z. We have a two-sample t-test if our sigma 1 and sigma 2 are not known. If it's known, we know our population standard deviations are known, which is very rare if you remember back, but sometimes we might have this. Then we're going to use that two-sample z-test in here. Now, for input, we're going to have to either select data or stats. Okay? Once again, if we know all our numbers, we know our mu's, we know our averages or our means in here, we can just go right into the stats. But if we only have data, okay, we're going to have to type it into a list and then bring those lists over in. Okay, if you remember, your TI 8384 has the L1, L2 list. In our NSPIRE, we would use our stat sheet, in which then we would type in, kind of like our Excel document, our list, and then we name it, then we bring that data over and in. And then we would run our hypothesis testing or confidence intervals based off of as we have in the past. Considering on now to part 2, once again, alternative methods. Okay. The two population standard deviations are both known or they are unknown, but we're assuming that they're equal. Okay. Once again, if they are known, okay, if sigma 1 and sigma 2 are known, okay, so we know what they are, we're going to be using that Z test. Okay. If sigma 1 equals, once again, we're assuming that this is. So we're assuming that they are equal to each other. We're going to be using that t-test. Okay, we have that t value for that hypothesis test in here. Now, do realize, assume that sigma 1 and sigma 2 are unknown. Do not assume that they equal each other, and use the test statistic and confidence interval given in part 1 of this section. So unless you are specifically told to do it a certain way, we assume that they are not equal, that they are not known, and then we go about our testing on here. So they have this nice little flow chart. Interference is about two independent means. First thing we look at, are sigma 1 and sigma 2 known? If they are known, we're going right into our other test. Once again, our Z test in here. If they are not known, we're going to ask, can it be assumed that they're equal to each other? Okay. If it can be assumed, now we're going to have to use a t-distribution with pooled standard error. If it's not, then we're going to approximate using our t-distribution, which is standard error. Okay, so there's a couple little difference in here on how this goes about. Once again, I would tell you this section right below here. Make sure to read through this. Basically, it talks about that if we use randomization to assign subjects to a treatment and placebo groups, we know that the samples are drawn from the same population. If we conduct a hypothesis test assuming that two population means are equal, it is not unreasonable to also assume that the samples are from a population with the same standard deviation. But we should still check that assumption. The advantage of this alternative method of pooling sample variances is the number of degrees of freedom is a little bit higher, so the hypothesis test has more power and confidence intervals are a little narrower. Consequently, statisticians sometimes use this method of pooling, and that is why we include it in this subsection. So basically allowing the pooling is a little bit more defined, a little more accuracy in there because you have that higher degree of freedom, but we never want to assume that we have this. Once again, if we're pulling from the same population, different groups, that overall population should be the same for everything, so we should have that, and that's why they could assume that they had the same standard deviation for each of those populations. But once again, realize that we have to be very careful with how we're working the tests and work the problems with what's known to us and what's given to us.